Now consider weak base equilibria. Okay, this equation is the basic equation for the weak base. Okay, as I said, you have to include this water. Okay, and weak base takes protons from water, um, and delivering producing hydroxide ion. So hydroxide ion, because of this species, the solution becomes basic. Okay. Here again, um, this one pH plus concentration may be approximately the same as OH minus. Okay, and let's set these concentrations X. Okay, and then the equilibrium uh, constant Kb is simplified as this one, right? And B is the obtained from the formal concentration. This is the mass balance equation. Okay, this is again the quadratic equation. All right, and then it can be completely solvable. Okay, here is the typical weak base problem. This is cocaine. Cocaine is base. Why? Because it contains this nitrogen atom here and non-bonding electron pair. This one now attracts proton. Yeah? It extracts a proton from water. As a result, yeah, this hydroxide ion is produced. Right? And Kb equals 2.6 times 10 to minus 6. Okay, this is Kb. But as I said, in this book, you cannot find Kb for cocaine from the appendix, but there is a Ka for this fully protonated form. Okay, you find this one, and then you can calculate the Kb for cocaine. Okay, anyway, in this condition, let's calculate the pH. Okay, the cocaine formal concentration is 0.0372. Okay, and it dissociates by X, and then after its association, B becomes smaller, by X. Okay, and then we set this equation, then we solve for X. Here X represents hydroxide ion. All right, and proton concentration is given by Kw divided by hydroxide ion, and which is 3.22 times 10 to minus 11, and pH is 10.49. Okay, and the fraction of dissociation is the concentration of pH plus divided by the formal concentration, which is 0.0083. Only 0.83% of base has reacted. All right. Okay, now consider this orthohydroxybenzoate. This one, we consider this one, this weak acid, and now start from this conjugate base. It reacts with the water, producing the hydroxide ion. Okay, in this case, uh, we set the concentrations X, okay, and we get this equation. So the Ka for this orthohydroxybenzoic acid is 1.07 times 10 to the minus 3. What about Kb? Kb is given by Kw divided by Ka, which is 9.3 times 10 to the minus 12. Okay. And in the meantime, for the para form, para-hydroxybenzoic acid, Ka is smaller than Ka for ortho form, but its Kb is larger than the ortho form. Okay, it's 3.5 10 to the minus 10. Okay, so here is a general statement. Conjugate base of the strong acid is the weaker base. All right. Okay, ammonia, right? This very small molecule, when dissolved in water, it becomes solution. It makes solution basic because it reacts with water, and producing hydroxide ion. Okay, as usual, we calculate Kb for ammonia from ammonium ion dissociation, from Ka, which is 1.75 times 10 to minus 5, okay? And this one, uh, when ammonia is what in water, it undergoes this equation, okay? And let's see. The initial concentration, formal concentration of ammonia is 0.1 molar, and we set this equation, and then we solve for hydroxide ion concentration, and it gives 7, and from this hydroxide ion, and then we calculate the proton concentration from KWN hydroxide ion, and it is 7.61 times 10 to minus 12 molar, and pH is 11.12. Okay, so ammonia gas is dissolved in water, the solution becomes basic. Very easy. Okay, now we enter buffer. Okay, you know this buffer is really important. It's extremely important. You see, and you have to understand the action of a buffer and how to prepare buffer solutions. Okay, what is buffer? Buffer, this word is used in many different areas. Okay, in electronics, the buffer means what? The signal, yeah, doesn't change. Okay, whatever the external, you see, after, if you use electronic buffer, and after the buffer, the circuit is very stabilized. Okay, but in chemistry, a buffer solution resists changes in pH. Okay, when acid or bases are added. Okay, buffer, that's the definition of a buffer. Okay, or pH doesn't change much when dilution occurs. Okay, so buffers resist the pH change. Yeah, this is important because in many cases, chemical reactions are performed at constant pH. Okay, so we need buffer solution. Okay, here let's look at this figure. All right, this is the pH dependence of the rate of cleavage of amide bond by enzyme chymotrypsin, okay, helping digestion proteins in intestine. Anyway, the point is that the enzyme chymotrypsin, no, is action. Yeah, this reaction rate changes with buffer solution pH. Okay, this activity is highest at pH 8 or around 8. Okay, at more acidic solution or in a more basic solution, the chymotrypsin activity decreases. Okay, so to make the chymotrypsin most active, the solution pH must be maintained around pH 8. Okay, in that case, the buffer is used. Okay, how do we prepare the buffer? Okay, let's study. Yeah, let's read this one. Naturally, buffer is made from weak acid and its conjugated base. Okay? This is general rule, but what if we don't have one of these components? Right? Yeah, we have a way. Okay, way to get around that problem. Okay, if mix A mole of weak acid with B mole of its conjugated base, the moles of acid remain close to A and the moles of base remains close to B. Very little reaction occurs to change either concentration. Okay, now let's consider this weak acid dissociation, whose pKa is 4.00. Okay, let's say the formal concentration of HA is 0.1 molar, and it dissociates to give rise to x amount of protons and an ion. Okay, and we can set this equation and solving this one, and then we can find the fraction of dissociation is around 0.031. Yeah, only 3.1% dissociates. All right. Well, as I said, buffer is a mixture of a weak acid and its conjugated base. Okay, it's a combination of HA plus A minus, or it's a mixture of a weak base and its conjugated acid B plus BH plus. Okay, now let's see how these weak, weak, the combination of weak acid and weak base, or combination of weak base and weak acid, yeah, this combination reduced pH change. Okay, you know, let's have a closer look at that. How does a weak acid or weak base operate to reduce pH change? Okay, let's consider the system of HA and A minus, and let's assume you add strong acid. Strong acid can be represented by H plus. Okay, this one, uh, when H plus is added, strong acid is added to the purple solution, and then since A minus is acid, this base, weak base, now this one A minus, this anion reacts with strong acid, and as a result weak acid is produced. Okay, HA slightly increases. Okay, because by the amount of added proton, the amount of HA is increased by this amount, while A minus, amount of A minus is slightly, okay, not greatly, but slightly decreases, but not much. Okay, okay, in the other case where the strong base OH minus is added, in the case a weak acid reacts with strong base to give A minus weak acid, weak base and water. So HA slightly decreases while A minus slightly increases, but not much. Okay, you understand now? Yeah? In this purple solution, although you add in a certain amount of strong acid or strong base, and then one of these components react with those strong acid or strong base. Yeah. And how do we treat this purple theoretically? Okay. Here is a very famous equation called Henderson-Hasselbalch equation. Okay. This equation is nothing special, but this equation is a simple rearrangement of equilibrium constant. Okay, let's first consider weak acid case. Okay, Ka is given by this one, and taking the logarithm on both sides. Okay, log Ka equals log this equation, and log Ka equals log proton concentration and plus log A minus divided by HA. Okay, so also by taking negative sign on both sides, then we get this one right here. So we put negative sign, and we negative sign here, right, and negative sign here. Okay, and then let me see, and finally we get this one is pH by definition, this is pKa by definition. Yeah, and this one is given. Okay, uh, so pH equals pKa plus log uh, A minus over HA. Okay, or using activity coefficients, okay, you can uh, write it this way. Okay, and here you're rearranging and then use change the position of these two. Yeah, this is the Anderson-Hasselbalch equation for weak acid and its conjugated base. Okay, yeah, this one. But what about you have weak base and its conjugated acid? Okay, again, it's very simple. You write the equation for Kb. Kb is given by this one. In this case, OH minus appears. Okay, and taking logarithm on both sides and change this to, and then minus log hydroxide ion concentration is equals minus log Kb plus this one. Okay, and this one is what? POH, and this is PKB. Okay, and plus log this term, it remains. And if we uh, what add 14, if we take a negative sign on both sides and add 14, and we get this equation. 14 minus pH is I'm sorry, 14 minus POH is pH. Okay, and 14 minus pKb is pKa plus log, and then since we put negative sign, this one is upside down. Okay, pH equals pKa plus log B over pH plus. All right. Yeah. This is the Henderson-Hasselbalch equation for the solution that is composed of weak base and its conjugate acid. Okay, the form is very similar. Okay, or you can memorize this form. Okay, or this form. It's up to you. Okay, so here is the properties of Henderson-Hasselbalch equation. When this one A minus and HA concentrations are the same, that means what? At first, you prepare HA solution and A minus solution, yeah, and then since this one the concentration is the same, and pH becomes pKa. Okay, at this pH, the purple capacity is the maximum. Okay, here you see pH. This is definition, and since what this one the concentration are the same, and log 1 is 0, so pH becomes pKa. All right. This relation is true because all equilibrium must be satisfied simultaneously in any solution at equilibrium. Okay, but in this case, it's rather rare case. Okay, let's consider what what if the one of these species concentration is 10 times or 100 times larger than the other species. Okay, here this table tells that pH, how pH changes depending on this ratio. Okay, when this ratio is 100 to 1, and pH becomes increased by 2. Okay, pKa plus 2. If change the ratio is 10 and pH is pKa plus 1, for 1 to 1 solution, pH equals pKa, and for 1 to 10 solution, pH equals pKa minus 1. For 1 to 100, pH equals pKa minus 2. Okay, this simple relationship, I think you can easily understand.